Hello and welcome back. Having discussed the concepts of electric field in the previous video, we are now ready to tackle a numerical example dealing with electric field. First, we'll determine the electric field at a couple of points near an electric charge, and then we will see what the force on new charges that are placed in these locations will be from the electric field at those points. Here's our example for today. I have a charge Q here that's minus 40 nanocoulombs that's sitting over here. And we want to determine first the electric field at points A and B. A is 20 centimeters to the right of the charge, and B is 40 centimeters to the left of the charge. As we recently discussed, the equation for the electric field at a point from a charge is given by K times the absolute value of the charge Q divided by square of the distance of the point at which we want the electric field from the charge. Now this only gives us the magnitude of the electric field, and for the direction we remember that if it's a positive charge it points away from it, and if it's a negative charge the electric field points towards the charge. Okay, with that in mind, let's calculate the electric field at these 2 points. EA is the electric field at point A, and that would be equal to the Coulomb constant K times the magnitude of the charge that's at the center from which we want to know the electric field, divided by the distance from that charge, and let's call this RA for point A, squared. Okay, the rest is just plugging in the numbers. We know that the Coulomb constant is 9.0 times 10 to the 9 Newton meter squared per Coulomb squared. I'll leave the units out of this setup here, and then I multiply it by the absolute value of the charge. Even though it's a negative 40 nanocoulomb, I'm only interested in the absolute value of it, so it'll be 40 times 10 to the negative 9 coulomb. I'm converting from nanocoulomb to coulomb so that the coulomb here would cancel the coulomb that's part of this constant. And then I would divide by square of the distance, and since the constant was given in Newton meter squared per Coulomb squared, I need the distance also in meters. So 20 centimeters is 0.2 meters, so I take 0.2 and then don't forget to square it. Okay, when you put all these into your calculators, you will get an answer of 9,000. And the units, after we cancel whatever we can from the units of these 3 numbers, would be Newton per Coulomb, which is the SI unit of electric field. Okay, we have a number now for electric field, but we got to remind ourselves we're not done yet. Electric field is a vector, and we do need to figure out the direction. In this case, the central charge is a negative charge, and when there's a negative charge, the electric field at all points will point toward the charge. So if I'm sitting at point A, and if I want to move toward the charge, that would have me moving to the left like this. So the electric field at point A would be shown as this vector. So now we're done. We know the magnitude of it, we know the direction of it, we have shown that in the figure, and so we have the electric field fully defined at point A. Now one other point I want to mention here real quick. Some of you are looking at this point A and saying, well, what charge sits there? So far there is no charge sitting there. I don't need to have a charge at point A for there to be an electric field at that point. Whenever I have a single charge, that charge will have electric field at all points around it, and I can figure it out at any point using this equation, and I don't need to have another charge sitting at those points. Okay, moving on, if I want to get the electric field at point B, I do the same kind of work. I've got EB equals K times the absolute value of Q divided by RB squared, the distance to point B. And this would be, once again, 9.0 times 10 to the 9 times 40 times 10 to the negative 9 divided by square of the distance. In this case, the distance is 0.4 meters. And I square that, and that's the setup. The numerator is the same as before because we're still talking about electric field from the same charge. The distance has changed, so that's reflected over here. And when you calculate this, you will get 2250 Newton per Coulomb. Once again, I have a magnitude, but I need a direction. And because the central charge is still a negative charge, I'm still going to have to point toward it for the direction of the electric field. And when I'm sitting at B, pointing toward the charge will mean pointing to the right. And since this electric field here is 1/4 of the electric field over here, the arrow length has to be 1/4 of what it is over there. So it would be something like this, a much shorter arrow, and this would be EB. Technically, I only had 2 significant digits in all of my inputs, so I should really round this to 2 significant digits, but I'm going to go ahead and specify all answers for this problem in 3 significant digits, assuming that these were specified to a higher level of precision than indicated over here. Okay, that's all we have to do in terms of determining the electric field, and we're done with that part of the question. Now, I want to add a second part to this question that says, if I now place charges at points A and B, what would be the force that those charges feel from these electric fields? So at A, I want to place a charge QA of minus 2.0 microcoulomb. And I want to know the force on this charge from this electric field. So in this case, the equation I need is this force on a charge equals the charge itself times the electric field. Here I want to use the sign of the charge. That'll give me the relationship between the direction of the force and the electric field. So when I do that over here, I've got minus 2.0 times 10 to the negative 6. Micro is negative 6, so I've converted that to Coulomb, and I multiply that by this 9,000 Newton per Coulomb, and remember that that electric field points to the left. And when I simplify this, I get an answer of 1.8 times 10 to the negative 2 Newton. And because it is negative of something that pointed to the left, so let me indicate this over here to carry the full vector meaning of this electric field, I would have this force now pointing to the right. Because it's multiplied by a negative number, the direction would flip. And so I can show that force like this. If I place QA over here, the force on that QA would point to the right like that. Okay, lastly, to wrap this up, let's say I want to place a charge QB at B of plus 4.0 microcoulomb. And I want to determine the force on it, so the force on charge B would simply be Q times the electric field at point B. So I've got these as vectors, and now my charge is a positive 4.0 times 10 to the negative 6 Coulomb. I multiply that by my electric field of 2250 Newton per Coulomb. The coulombs will cancel. I'll get an answer in Newton of 9.0 times 10 to the negative 3 Newton. And since I've got a plus and this electric field here was pointing to the right, the force also would be pointing to the right. So I can show that over here as I'm going to offset it a little bit to the bottom. So if I have QB sitting over there, the force on it would be something like that, FB. And this was FA over here. And by the way, you could have used Coulomb's law, which if you remember was the force between two charges was given as K times absolute value of Q1 times absolute value of Q2 divided by R squared. You could have used that to find the force between this charge Q and QA, as well as this charge Q and QB. And you would get the same answer, and for practice it might be a good idea for you to verify that. But once we find the electric field, there's really no reason for us to go back to Coulomb's law. We can simply use the electric field to find the force on a charge that's placed at that location. While I'll let you figure out the numerical forces through Coulomb's law if you want to using these charges, let's quickly verify the direction of the forces. So this charge in the middle was a negative charge, QA was a negative charge. So the force between those two charges would be repulsive, which means charge Q would push QA away and so to the right. And that matches what we got. And if we look at the other charge, Q is negative, QB was a positive charge, the force there would be attractive, which means charge Q would pull QB toward it, so to the right, so that direction of force matches as well. So even though the direction of electric fields was always pointing toward the charge, the direction of forces can change based on the sign of the charge itself, and so all of that ties in pretty nicely. In this slice of physics, we worked with a numerical example dealing with electric field. We determined the electric field at a couple of points near a negative charge, and then we used that electric field to figure out what the force might be on a charge if they were placed at those locations. Thanks. See you soon.